In the early 1980s, the center of the personal computer universe was a pair of Intel chips, the 8086 and its cheaper sibling, the 8088. They powered the IBM PC, the growing wave of compatibles, and they set the rules for what a PC even was. If you wanted to run PC software, you ran it on Intel. But in the background, something unusual was happening. In Japan, engineers at NEC were quietly building a processor that could pretend to be an Intel 8088. Same pins, same instructions, yet run programs faster, cooler, and with a few tricks of its own. To most users, it would look like the same old PC. Under the hood, it was anything but. This chip was the NEC V20, and its 16-bit sibling, the V30. They would end up in Japanese business machines, in oddball Western PCs like the Tandy 2000, in industrial controllers, and even years later in arcade and console hardware like SNK's Neo Geo, doing support work behind the scenes. The V20 story is about more than just a clever upgrade. It sits at the crossroads of corporate alliances and lawsuits, of microcode and compatibility, and of a brief moment when x86 wasn't yet synonymous with a single company's name. To understand how NEC pulled this off, we have to rewind to the world before the V20 existed. By the start of the 1980s, Intel had already transformed from a memory company into the keeper of the mainstream microprocessor roadmap. The 8080 and 8085 had defined much of the 1970s hobbyist and early microcomputer scene. The 8086, introduced in 1978, pushed the architecture into 16-bit territory. When IBM unveiled the original IBM PC in 1981, powered by the cost-reduced 8-bit bus 8088, it unintentionally crowned Intel as the default CPU supplier for what would become the global PC standard. The 8088's segmented 20-bit address space, quirky instruction set, and performance limitations didn't matter as much as the simple fact that major software developers were now targeting that platform. Meanwhile, the wider industry still worked under a model where second sourcing was common. Big customers didn't want to rely on a single factory or a single company for such a critical component. So Intel signed deals with other manufacturers, allowing them to produce Intel-compatible chips under license. NEC, one of Japan's leading electronics giants, was among those partners. NEC already had deep semiconductor experience. Under its agreements with Intel, it fabricated genuine Intel-compatible 8086 and 8088 parts as a second source. This gave NEC not just legal cover to work with x86 designs, but also an intimate understanding of how these processors behaved, and, importantly, where they could be improved. As IBM PC compatibles began to spread and Japanese PC makers were charting their own paths, NEC faced a choice: remain simply a licensed second source, or use its expertise to design something more ambitious. Inside NEC, engineers set out to create their own implementations of Intel's 16-bit architecture, the V20, aimed at the 8088 socket, and the V30, targeting the 8086 pinout. The goal wasn't to break compatibility, it was the opposite. Make a chip that could be dropped into existing systems with no board changes, yet offer a tangible performance upgrade. That meant meticulous attention to pin-level behavior and to the externally visible timing of the bus cycles. A V20 had to look to the motherboard and its chipset exactly like an 8080, but NEC was free to change everything behind that interface as long as software saw the same results. They redesigned the internal microarchitecture and microcode, the low-level control sequences that implement x86 instructions. While Intel's original designs were constrained by earlier process technologies and a conservative schedule, NEC could take a fresher approach: tighter microcode, more efficient internal data paths, and more aggressive use of their then-modern manufacturing. NEC also took the opportunity to tack on something unusual: an 8080 emulation mode. With the right software trigger, the V20 and V30 could switch personalities and execute Intel 8080-style instructions in hardware. For markets with a large base of 8080 or Z80 code, particularly in Japan and in embedded systems, this was a powerful compatibility hook. Public sources differ on how much, if any, Intel reference microcode NEC had originally seen versus what ended up in the shipping V-series chips. What's clearer is that by the time these processors reached the market, NEC had invested heavily in its own implementation, a fact that would become central in the courtroom. Compared directly to an Intel 8088, the NEC V20 was not a radical new architecture. It was a more polished rendition of the same instruction set. The improvements showed up in the details. Instruction throughput was generally higher. Many common instructions completed in fewer internal cycles, which translated into faster execution at the same clock speed. Integer multiply and divide, traditionally slow on early x86 chips, were noticeably quicker on the V series. For software doing a lot of arithmetic, graphics operations, certain business calculations, and later some games, this made a real difference. The 8080 emulation mode set the V20 apart from a typical clone. Instead of requiring a separate 8-bit CPU for legacy code, system designers could rely on the V20 to run both x86 and 8080 style software. This found its way into configurations where old code libraries, development tools, or peripheral controllers still expected 8080 semantics. In practice, benchmarkers in the 1980s often reported speedups on the order of roughly 10 to 30%, compared to a same clock 8080 in many real-world tasks, sometimes more in specific synthetic tests. Exact numbers varied by workload and system, but the perception among enthusiasts was clear. A V20-equipped XT felt snappier. NEC's manufacturing process also gave the chip an edge in power and heat. For portable machines and tightly packed desktops, a cooler-running, slightly more efficient CPU with better performance was a compelling drop-in upgrade. All of this came while maintaining strict software compatibility. DOC's BIOS calls and application programs written for the 88G generally ran unmodified, revealing the V20's enhancements only through their improved responsiveness. As NEC's V-series processors entered the market, Intel grew increasingly uneasy. On paper, NEC was a licensed second source, allowed to manufacture Intel-compatible parts. But Intel argued that NEC had crossed a line. It claimed that NEC's microcode, the internal control patterns that make the CPU execute its instructions, infringed Intel's copyrights. This dispute escalated into a major legal battle in the mid-1980s. At stake was more than just one line of chips. If Intel's view prevailed, it could set a precedent that any compatible microprocessor with similar microcode behavior might be vulnerable to copyright claims, chilling the entire practice of producing near drop-in replacements. NEC countered that its V-series microcode was independently developed, and that while its external behavior matched Intel's by necessity, the internal implementation was its own work. Courts had to grapple with a tricky question. How much of a processor's internal design could be protected as creative expression, and how much was simply the inevitable result of implementing a published instruction set? In the eventual rulings, U.S. courts largely sided with NEC's position. They acknowledged that microcode could, in principle, be copyrighted, but they found that NEC had not simply copied Intel's work, it had created a legitimately independent implementation aimed at compatibility. Legal scholars still debate some nuances of this case, but its practical outcome was clear. It established that building a compatible processor, even one that mimicked the behavior of another at a detailed level, was not automatically an act of copyright infringement. That precedent would echo into future disputes in the semiconductor world, including later x86 compatibility fights. While the court case played out, NEC's V20 and V30 chips were quietly finding homes. In Japan, NEC was a major force in the domestic PC market with its PC98 series. Although many PC98 models used other NEC-designed CPUs like the 8086-compatible 8086 derivative Mu-PD, 8086 or later, 286 and 386 class processors. The exact extent of V-series use across the long-running PC98 ecosystem is a bit muddled in surviving documentation, but V20 and V30 parts did see deployment in various Japanese business and industrial systems where x86 and 8080 compatibility both mattered. In the West, one of the more visible adoptions was the Tandy 2000, released in 1983. It used the V30 as its CPU, running at higher clock speeds than a typical IBM PCXT and delivering noticeably better performance. However, the Tandy 2000 was not fully hardware compatible with IBM's design, which limited its ability to run the growing library of PC-compatible software, despite its raw speed advantage. Beyond flagship machines, the V20 was particularly attractive in embedded and control applications. Manufacturers could design boards that spoke PC at a high level, while also handling older 8-bit style tasks using the 8080 mode, all with a single chip. Perhaps the most surprising chapter of the V20's life came later, in the arcade and console industry. SNK's Neo Geo hardware, introduced in 1990, used a V30 as a secondary processor in some configurations, often for tasks like sound control or subsystem management, alongside its main 68,000 CPU. Other arcade boards from the late 1980s and early 1990s occasionally employed V-series chips in support roles, sometimes leveraging that 8080 emulation mode to reuse existing codebases. Most players standing at an arcade cabinet or in front of a Neo Geo console never knew that some of the system's work was being done by a descendant of the humble PCX TPU, wearing NEC's badge instead of Intel's. For many home users and hobbyists in the late 1980s and early 1990s, the V20 was less a design and component and more a secret weapon. If you had an IBM PC or XT, or a compatible machine with an 8088 socket, a V20 offered one of the cheapest speed boosts imaginable. Swapping an 8088 for a V20 was, in many systems, as simple as carefully pulling the old chip and inserting the new one. No soldering, no new motherboard. Enthusiast magazines and bulletin boards circulated benchmark results and compatibility notes, and a small cottage industry of upgrade kits formed around the chip. Users reported smoother performance in everyday tasks, marginally faster spreadsheet recalculations, and in some cases better frame rates in the growing library of PC games, all while keeping the same clock speed and overall platform. For those who couldn't afford a jump to a 286-based system, the V20 felt like a bridge that extended the useful life of older hardware. The 8080 emulation mode also had a second life among hackers and homebrew developers. It opened up curious experiments with running CPM-style software or repurposing old code on newer PC platforms. Modern retro computing projects still occasionally play with this feature, using V20-equipped boards to demonstrate the continuity from 8-bit to 16-bit software ecosystems. Today, the V20 holds a special place in the vintage PC community. Collectors seek out original upgrade kits, and some modern clone boards even design their sockets with the V20 in mind. It's remembered less as a mass-market standard and more as a clever tweak for those who knew where to look. Looking back, the NEC V20 and V30 occupy an unusual niche in computing history. They were not the dominant CPUs of their era. That role remained with Intel's evolving x86 line, and later with competitors like AMD, under formal cross-licensing deals. Yet, the V-series proved that a company outside Intel could build a compatible, in many ways superior implementation of the same instruction set and survive the legal fallout. The Intel NEC Microcode case helped clarify that compatibility itself was not a crime, setting boundaries that would matter when other firms implemented x86-compatible cores, and later when legal battles over licensing and reverse engineering flared up. Some historians see a through line from this case to the climate that allowed AMD to pursue its own x86 designs, and to the broader acceptance of cleanroom reverse engineering as a legitimate path. On the technical side, the V20 foreshadowed a pattern seen later in the industry: alternative implementations of a popular instruction set that focus on efficiency, power, or specific features rather than raw headline speeds. In a way, the V20 was an early example of treating an ISA like x86 as a common language, not a single-vendor monopoly. Culturally, the chip's afterlife has been sustained less by corporate marketing and more by enthusiasts, archivists, and retro hardware tinkerers. Documentation scans, dive photos, and long-running forum threads keep the technical details alive, while stories of XT upgrades and oddball machines like the Tandy 2000 give the V20 a human dimension. In a PC world that gradually converged on stricter standards and fewer CPU suppliers, the NEC V20 family stands as a reminder of a looser, more experimental phase. It shows how, for a brief window, being IBM PC compatible didn't automatically mean Intel inside, and how one company's attempt to better the standard quietly left its mark in courtrooms, circuit boards, and in the memories of those who made their old machines run just a little bit faster.